Hello differential equation students. In this section we'll talk about how do we solve higher order linear differential equations with constant coefficients that are non-homogeneous type. So in this section we're going to take a look at some basics, and then we will solve. If you have time, then we will solve an example. Otherwise we'll do it in the next video. So if you take a look at in solving higher order linear differential equations with constant coefficients, we need to understand some basics. So to do that, let me say this first. In mathematics, there are three types of maps: Apple Maps, Google Maps, Bing Maps. I'm just kidding. So those three maps are functions, functionals, and operators. What do I mean by that? So you all know functions from, you've been studying about the functions for a long time. So if you recollect the functions, that's a mapping. So you have a domain and you have a range, and the functions are basically the functions of numbers, right? Functions of numbers, and it takes one element from your domain to another element in your range. In your range, if this is your range, and if you call this is x, this function f takes this x to some sort of a y right there. So let's just say this is your y, and this is what we call a function f. So we write it usually this way, that y is equal to f of x. So that means you input your x into the function, it gives you the output, and we call that output as the y, right? So basically the functions are the one that takes numbers to numbers. For example, if you give you an example, that is f of x is equal to, let's just say as simple as the f of x is equal to x squared. This f is a function from a set of real numbers from negative infinity to infinity, and gives you values in 0 to infinity. So if I feed in 1, it's going to give me 1 squared, which is 1. If I feed in negative 1 to the function, it's going to give me negative 1 squared, which is also 1, and there's something called 1 to 1, on to, and so on. So but we don't have to worry about those things now. And the second type of mapping, and by the way, this is called mapping, right? This is called mapping. F maps x to y, right? That's what I mean by f maps x to y. X to y right there, right? Now the second, so in this functions, it takes numbers as the inputs and gives you numbers as the output, right? Again, without getting too much into theory, so what is a functional? The functionals are basically another type of functions, another type of maps. So it takes inputs as set of functions and gives the output as numbers, right? Output as numbers. For example, so the functionals are simply speaking, I'm missing a lot of theory in here, right? So simply functionals, right? Simply speaking, it takes functions as inputs, and numbers as outputs. So for example, let me define a functional. I'm going to call this functional, just say the functional r. This r of f is equal to, let's just say 0 to 1 f of x dx. So if you feed in a function, it's going to, it's a definite integral, so it's going to give you a number. For example, if I feed in the function r of x, right, let's just say if I'm feeding the function x squared, right, x squared is a function, and what I'm going to get 0 to 1 x squared dx, which I integrate. This is going to be x cubed over 3, and my lower limit is 0, upper limit is 1, and if I do that, I'm going to get 1/3. So when I plug in x squared into this function, and gives me 1/3 as my output, so that's called functional, right? So these are called functionals. Another functional would be, for example, let's just say d of f is equal to the derivative of f with respect to x at x is equal to 0, right? So for example, in here, if I give d of x squared, that is going to be the derivative, which is 2x, and I'm going to suppose to plug in x equal to 0. When I do that, that is going to give me 0, right? So again, I'm feeding in a function, and I'm getting numbers as the output. So you see that, right? So that is called functional. So those things, I mean, you already know about the functions before. You're now we just talked about functionals. We're not going to use this very much, but what we are going to use very much in this section is that operators. So what are these operators? These operators takes functions as inputs and gives you functions as outputs. So the operator takes functions as inputs, functions as outputs, right? So for example, what do I mean by that? So let's take a look at the operators. These operators, for example, I'm just going to say T of f, which is equal to, I'm just making this up, right? Just f squared. So now if I feed in the function x squared into this, it's going to give me x to the 4. The point here is I'm inputting a function and I'm getting my output as a function, right? So let's take a look at another one. T of f is equal to integral 0 to x f of s ds. So in this case, suppose if I say t of x squared, then this is going to be integral from 0 to x s squared ds, which would be x cubed over 3. Again, I am feeding in a function. I am getting another function back as the output, right? These are called this is called operator. Let me give you one more that's most important for us. D of f. This is the very important one that we're going to use it often and often. What is the d of f? Let's just say this is simply f prime of x, the derivative of x. So for example, if I feed in t of x squared, and that is going to give me simply the derivative of x squared is 2x. So that's another function. So I'm feeding in a function as my input. I'm getting a function 2x as an output. So x squared gives me 2x. So that's the one. And the derivative, as you see here, the derivative of the function now acts as an operator. So now, again, for our purposes, these operators are the very important things, and that's what we're going to talk about more in this one. Now, what are those operators? Before we talk about the operators, I want to talk about one property of the operator that are very, very useful, that are wonderful. It doesn't happen every single time, but whenever it happens, it's awesome. So what would that be? That's called linear operators. So what are those linear operators? If an operator, I'll just say that let's denote it as a T. If it satisfies these two conditions, as a matter of fact, you can combine them as a single condition. I'll talk about it in a moment. For example, when you have two functions f1 and f2, remember the operators are, you feed in functions, you get the functions out. Functions in, functions out is your operators, right? Functionals are functions in, numbers out. Functions are numbers in, numbers out, right? So I have two functions. Let's just say I'm adding these two functions, and the output, if it's exactly same as the operator t operator on the f1 plus the operator t operator on the f2, right? That will be a linear, that will be one condition of the linear operator. The second condition is the following, which is if you have an alpha that you're multiplying with a function and you operate it, right? And then what happens is, if that happens to be alpha times the tf, right? And here alpha is a constant. Alpha is a constant or a scalar, whatever you want to call it, right? Alpha is a constant. If these two properties are satisfied, we call that operator t. We call this operator t as a linear operator, right? We call that as a linear operator, and that's very, very important. That's a wonderful property that we will make use of it very well. These two conditions can be summarized into a single condition, and that is the following. If t of alpha f1 plus f2 is equal to alpha t of f1 plus t of f2, then we say it's a linear operator. Let me give you a couple of examples. The number one example, I think, let me give the one that we will use the most. Let's just take a look at the derivative operator, right? The d, you know, the way that we define df is equal to f prime, right? So if you take a look at this one, the derivative of alpha f1 plus f2, as you all know, the derivative of the two functions is same as the sum of the derivative of sum of two functions is same as the sum of two derivatives of the function. So this is going to be d alpha f1 plus d f2. And we also know if you have a constant with respect to the derivative, you can pull it out. So this is going to be alpha d of f1 plus f2, d of f2, right? And that's the and it satisfies the property of the linear operator. In other words, if you want to say, by the way, you can say this is the same as saying, alpha f1 plus f2 prime is equal to, as you know, this alpha times the f1 prime plus f2 prime. And this is exactly same as that one. That's exactly same as that one. So it's a linear operator. So the derivative operator, I want you to pay attention here very closely. The derivative operator that we know, right? The derivative is actually a linear operator. Similarly, by the way, this also, the integral operator that we talked about earlier, was also a linear operator. But what about this one? I'll let you go home and verify. That is not a linear operator. As a matter of fact, it does not even satisfy the first condition, or even the second condition. In this case, it doesn't satisfy. For example, let me use a different color. So for example, if you take a look at that operator, we call it as TFF, as f squared 1. If I say t of alpha, or 2 times x squared, if it's a linear operator, you should have 2 times t of x squared. But unfortunately, if you take a look, what we are going to have is, we're not going to have that. So if you really see, what we're going to have is, we are going to have, this is 4 times x squared the whole square, 2 times x squared the whole squared, which is 4 times x squared, which is not equal to that, because this is equal to 2 times x to the 4. So you see that 4 times x squared is not equal to 2 times x to the 4, by the way, is not equal to that. And so therefore this is not a linear operator. So here is an example that is not linear, and these two are, this is a linear operator, and this is also a linear operator. So this is a linear, this is a linear, this is not a, it's a non-linear operator, if you want to call it. All right. So now, as I've said earlier, the derivatives are linear operators, right? So the derivative satisfies the definition of a linear operator. So that's a wonderful, good news for us. Now, so therefore, so as I said earlier, so therefore, what do we have here is, if you have the function d of f, which is the f prime. So if you have a function, your p feeding in y, it's going to be y prime. And by the way, not only the first derivative, this is the first derivative, right? Not only first derivative is a linear operator. What about the second derivative? What about, the second derivative, which is d, which we write, let's just say for the second derivative is this, right? By the way, second derivative is d of f, right? Because this is a function, I can feed in that function to the operator. That's going to give me a function which is going to be the derivative of f prime. The derivative of f prime is f double prime, right? So if you say, in other words, d of y is going to be y double prime, right? That is also a linear operator, you can verify. Not only that, what about the d cube? So by the way, for this I'm going to say, rather than saying this one I'm going to say in the future, d squared f, or this I'm going to say d squared y. So by the same token, if I go with the d cube, if I go with the d cube, what do I mean by that? D cube of y, by which I mean d of y. I can do that. The reason, because the operators are the inputs are functions, the outputs are functions. So that's a function, I can input it inside, which is a function that's I can input it inside. So we are okay over there. All right, now let's take a, so therefore that's same as saying, by the way, y triple prime. In general, the nth derivative dn of y, right? dn of y, which is d of you have totally n number of them, right? Totally n number of them. You're going to have another d of y, right? and that is the y nth derivative of y. That is also would be a operator, and not only they are operators, they are also, this also linear operator, this also linear operator, this also linear operator, this also linear operator, and we verified this. You can verify that. So the derivatives acts as the linear operators. And so therefore what we can do now, is it possible to write the differential equations in the operator form, right? Is it possible that we can do that? Let's take a look at this very simple derivative. And by the way, before I go, I want to quickly talk about one thing. When we say this, right, when we say this in here, when we say these things in here, right, when we call it as a d squared, right, there's another way you can write it, and that another way would be, for example, another way would be, right, this is d of y is, by the way, is same as saying d composed with the d of y. That's what we have, a d square, right? So this d cubed is, right, the same as saying, this one is same as saying, by the way, d operated with the d operated with the d, in other words, composed with the d of y, right? And that's a composition of functions, right? So this is going to be what we call d cubed of y, right? So something that you need to know. All right, so now let's take a look at the differential equation in the operator form. So suppose you have a differential equation y prime minus y equal to 0. Very simple differential equation, right? Very nice differential equation. How do I write this in the operator form? You see, this one is same as saying d of y. And what about this, right? So there's another operator, and that is called the identity operator. What this identity operator does is the following. So we say this is I of y. And what is it, I of y? I of y is, it gives the same functions back, you see, right? That's it. It doesn't do anything to the function. It gives you the same functions back, and that is called the identity operator, right? So you see that it takes functions as input, functions as the output, and gives you that, right? So we can write this one as, if you don't mind, as this one, right? You can write this one now as I of y. We can write this as a I of y, right? That's coming off of there, right? So let me write it down. So this is I of y, and now this is an operator, that's an operator, this is the same function, these two are same function. So now what I can do, I can write the following, and that is d minus I of y, right? D minus I of y. This 0, you can say this is equal to 0. There is some small thing in here, but that's a 0 over there. This 0 is no longer as a number. Now this 0 is a function 0. So there's also another operator called 0 operator. 0, not O. If you want to call it as O, that's fine. O of y is basically 0. That's also a linear operator, by the way. That's also a linear operator. And this is also a linear operator, and this is also a linear operator. This is a linear operator, right? This is also a linear operator. So it satisfies these two conditions. It satisfies these two these two conditions, or you can say this one condition, it satisfies that. So those two are linear conditions. So when we write in the operator form, right, this is called the operator form, right? When we write it in this way, this side is no longer the number 0, right, that you have here. But this is also number, is not number 0, that's also a function, by the way, right? That 0 right there is a function, is not a number. And so this is a if you want to call it, you can think of it as a 0 operator there. All right, so this is called operator form. This is called the operator form. So if you, this is called the operator form. And if you want to write it this in a different way, it's okay to say that. I think in the future that's what I'm going to do. I'm going to simply say d to make our life easy. I'm going to say 1 of y. I'll tell you why in a moment, why that'll be very useful for us, right? And this is called the operator form. Again, from operator form, we can go back to the equation. What do we mean by this? This means this is d of y minus 1 of y equal to 0. D of y is y prime, 1 of y is y equal to 0. So we get this original differential equations back, right? Now let's take a look at this one. What would be the operator? What would be the operator form of y double prime plus 2y prime minus y equal to 0? What would that be? That would be d squared of y, because the second derivative, plus 2 times the d of y, that's the first derivative, minus I of y, or you can say 1 of y equal to 0. And so therefore, if you want to write this in the operator form, that will be d squared plus 2d minus I, or you can say 1, either way is okay, of y, function y is equal to 0, right? That's the operator form. Let's take a look at another one. So how do you write this one? Y double prime plus 2y prime plus 5y equal to 0. How do you do that? Well, this you can say this is, d squared y plus 2dy plus 5iy equal to 0. This we can say d squared plus 2d plus 5i of y equal to 0. That's why I said, initially, if you recollect, I said I would like to write this as a 1 of y rather than saying I of y. I would like to write this 1 of y. So therefore, rather than writing 5i, it's customary to write it as the following. It is customary to write this one as d squared plus 2d plus 5 of y equal to 0. So whenever there is nothing in here, we assume that's an identity function. If it's a constant by itself, we assume it's an identity function, and this is called the this is the operator form of any differential equation. So anything that you have, you can write it in terms of operator form. All right. So now from a differential equation, we know how to convert it into an operator form, right? We know how to convert it into an operator form. So if you really take a look, the characteristic equation that we talked about earlier, right, in the previous section, that right here, that we talked about, the characteristic equation right here, right? That comes, as a matter of fact, that comes off of your, in some sense, it comes off of your operator form. So if you have a differential equation, that is, let me just copy this. If you have a differential equation, right, whose operator form is d squared plus 2d plus 5 of y equal to 0, and the characteristic equation that we learned earlier in the previous section is m squared plus 2m plus 5 equal to 0, right? You see that. So they're all, interrelated. Differential equations, operator form, and the characteristic equations are all, they are all interrelated. So if I give you another differential equation, which is, let's just say, y to the 2020, the derivative, plus 15 y to the 53 and 2y squared, or second derivative, 2y prime y double prime equal to 0, whose operator form would be d to the 2020 plus 15d to the 53 plus 2d squared of y equal to 0, and whose characteristic equation would be m to the 2020 plus 15m to the 53 plus 2m squared equals 0, right? Equals 0. That will be your characteristic equation. So that's how we can write the characteristic equations. I'll let you give me 2 more examples, right? I'll let you do this on your own. Give me 2 more examples, right? 2 more examples on your own. 2 more examples of your own differential equations whose operator form and the characteristic equations. Now let's take a look at what we call annihilator. So what is this annihilator business? So what is this annihilator? So if you have an operator t, and this operator t, when you feed in f, right, when you feed in f, this operator makes the f 0. It gives you an output as 0, right? Then t is called the annihilator of f, right? If that happens, right, then t, the operator t, is called an annihilator of f. So it's basically decimates, right? It makes it 0, so it sends you back to 0. So we call that as an annihilator, right? Of f. So for example, if you give for the derivative operator the function 1, the function constant function 1, it makes it 0. So we say the derivative operator d is an annihilator of a function f of x is equal to 1, right? We can say that it's called the annihilator. Similarly, if you take a look at the d squared of x, the second derivative of x is 0, right? So you can say the d squared is an annihilator of the function f of x is equal to x and so on, right? These are called annihilators of an x right there. Now let's take a look at this one, right? D squared, d minus I, right? If you take a look at what happens to the e to the x, right? If you take a look, this is going to be d of e to the x minus I of e to the x, right? The derivative of the e to the x is e to the x, and the identity function is, the e to the x, which is equal to 0. That means d minus I is an annihilator of e to the x, right? So d minus I is an annihilator of e to the x. So I want you to pay attention to this. So this tells you d minus 1 or I, right, is an annihilator of e to the x, right? So that reason because d minus I of ex is equal to 0. Similarly, if you take a look at the d minus 2, or I don't have to write it down, but just in case for the sake of clarity, d minus 2I of e to the 2x, what happens to that, right? Let me quickly show this. So this is the d of e to the 2x, that is the derivative of e to the 2x, which you all know is 2e to the 2x minus 2 times I is by itself 2e to the 2x, and it's going to give you 0. That means I can say d minus 2I is an annihilator of e to the 2x. As a matter of fact, ladies and gentlemen, this is, what is the differential equation? What is the corresponding differential equation of this? The corresponding differential equation of this is in the operator form. That's in the operator form. So y prime minus y is equal to 0. As you know, this e to the x, this guy right here, the e to the x, is a solution to this differential equation. So it's not like annihilator is something irrelevant. As a matter of fact, if d minus I, if the operator form annihilates something, whatever it annihilates happens to be the solution to the corresponding differential equation of that operator form, right? So that's very, very, very important for us. This is same as asking the following question. So when you try to find the solution to this nice wonderful algebraic equation, x squared is equal to 1, what do? You rewrite it as x squared minus 1 equal to 0, where you keep the 0 on the other side. Then you ask yourself a question, what values of x would be a solution to this? And then that's going to give you, well, when I plug in x equals 1 or x equals -1, that's going to give me a solution to this, right? So that is, so these are basically the annihilators of this algebraic equation. This is an annihilator of that. So this equation is an annihilator of that particular number. So those happens to be the solution of that equation. Similarly, if you have an operator form, if you have an operator and something is and if this operator annihilates something, right, then that whatever that function happens to be the solution to the corresponding differential equation of that operator form. So now in general, ladies and gentlemen, if you really look at the pattern, now I can, as a matter of fact, write down this as in general, that d minus mi d minus mi of e to the mx, right? You know, that's going to give me a 0. So therefore I can say d minus m I is an annihilator of e to the mx, right? And what would that mean? That would mean, this would mean that e to the mx is a solution to y prime minus my equal to 0. And we have seen this earlier, right? We have seen this earlier. So that is the the relevance between the relationship between the operator annihilators and the characteristic equation and the solution of a differential equation. Now let's take a look at this, right? Now let's take a look at this. So in general, when you have this form, right, we know that this is, we know that, then you know this would be a solution to that, right? Now let's take a look at the second order. These are, we are looking at the first order. Let's take a look at the second order. Let me change a different color. Let's take a look at this differential equation. Y double prime minus 3y prime plus 2y equals 0, right? Now, what is the operator form? The operator form would be d squared minus 3d plus 2. I'm going to say, I'm going to skip the I part in here of y equal to 0. And by the way, and if I can rewrite this in the composition form, which would be d minus I, or 1, which is same as saying d minus I, composed with d minus 2i, or I can simply say d minus 2, of all of that operated on y. All of that operated on y. You all know this very well. You all know this very well. And that is d of 0. The derivative of 0 is 0, correct? The derivative of 0 is 0. So if you have something, the d of, let's just say 1, right? That's going to be a 0, correct? Because this is going to be a 0, and then if you find the derivative of that, that is going to be a 0. So therefore, if this, whatever that you have, if this d annihilates 1, if the d annihilates 1, then d of that is also going to annihilate 1. Not only that one, any operator is also going to, any operator of this form, d minus mi, or I don't know, alpha I or ki, let me put ki, let's just say ki of 0 is always going to be 0, right? So if an operator is already annihilates something, whatever you operate again with any other operator, any other derivative operator of this form, is going to make it 0, right? If you have an operator already that made something is 0, and any operator that you have, right, that's going to make this a 0, right? So therefore, if something is an annihilator of this, and if you do this, right, something is an annihilator of this, and then if you operate this further on, it's going to make it 0. By the same token, right, we can say here if something annihilates this, is going to annihilated by this also. And by the way, in this case, this in general the composition is not commutative. In this case, it's a linear, it's an operator. In this case, it's a derivative operator. In this case, it's a commutative, so you can go back and forth. And so therefore, by the way, this d minus 1 we know is going to annihilate e to the x, and this d minus 2 we know that it's going to annihilate e to the 2x. How do we know that? We just learned right here, right? We just learned right there, right? So therefore now I have two of them. And so therefore we can say this whole thing, right? The entire differential equation, which is in the operator form, is going to annihilate this and this. What do I mean by that? If I feed into this operator, is going to make it 0. If I feed into this operator, it's going to make it 0. You can verify that later, right? You try to feed into this and see what happens. You try to feed into this and see what happens. It's going to make it 0. I'll do the one and then I'll let you do the other one. So for example, what do I mean by that is, if I feed in e to the x to the d squared minus 3d plus 2, what that means? That means the second derivative of e to the x minus 3 times the first derivative of e to the x plus 2 times the I, or I'm just going to simply say 2 times the e to the x, which is, by the way, second derivative of e to the x is e to the x, minus 3 times the first derivative of e to the x is e to the x, and plus 2 times e to the x. As you see here, this is 1 plus 2, which is 3. 3 minus 3 is equal to 0, and that gets annihilated, right? You verify this one on your own. So that's an operator that makes it 0, right? Now I want to say one other thing. I want to quickly bring one other theory in here, which is the following. In general, if you have a linear operator that has this wonderful, amazing property, and what is that property? And the property is the following. The property is, if you have f1 and if you have f2, right? If you have f1 and if you have f2, and if an operator makes the f1 0, if an operator, that same operator makes the f2 0, right? What can you say about t of f1 plus f2? We know that it's a linear operator, so therefore if it's a linear operator, therefore we know that this is t of f1 plus t of f2, right? Because it's a linearity, and the first one is 0 because of this, the second one is 0 because of this, so therefore the whole thing is 0. And not only that, by the way, if you have any constant times the f1 plus another constant times f2, what is going to happen to that? Again, by the linearity, this is c1 times t of f1 plus c2 times the t of f2, right? And again, this is going to be 0, so anything times 0 is going to be 0 anyway, and this is going to be 0, so any constant times that is also going to be 0, so the whole thing is 0. So in general, what we're going to have is, the following, that if you know two functions which are going to be annihilated by one operator, any linear combination of these two, what do I mean by the linear combination? This is what I mean by a linear combination. A constant times the function plus another constant times the function is what we call the linear combination, is also going to get annihilated. So what do I mean by that in this particular case? In this particular case, if you call this operator t as d squared minus 3d plus 2, then this t of a constant times e to the x plus another constant times e to the 2x is going to go to 0. Right? So because of that, so in general, if I summarize, what do I have? I have the following. If c and phi are such that t of c equal to 0 and t of phi equal to 0, then t of c1 phi plus c1 c plus c2 phi is going to be 0 for any constants, c1 and c2. And this is called the linear combination of c and phi. The c1 phi1 plus c2 phi2 is what we call the linear combination of the functions c and phi, right? And this is a very, very important property, and that's what makes it to say, in the earlier, whenever we have this, then the solution is this. Whenever we have this, the solution is a linear combination of all those four functions, right? That's what makes it to say. We'll talk about in a moment about a few other things in here. So that's number one. So now let's try to summarize. What do I have here? I want to quickly summarize something in here. So if you have an annihilator, if you can rewrite the annihilator into this one, if you can rewrite the annihilator into if you can write on the annihilator, if you can write the operator into this form, and the d minus 1 is an annihilator of this, d minus 2 is an annihilator of this, then this the composition of these two annihilators, which is this one, which is the operator form of this differential equation, right, is going to annihilate any linear combination of that, right, any linear combination of that. So going back to what we did earlier in the previous video, now I can summarize the following. And what is its summary? And that summary would be that e to the mx would be annihilated by d minus mi. In other words, let me rewrite it the opposite way. That d minus mi is an annihilator of e to the mx, and d minus m I, I'm going to say simply m, right, to the k. When I have a k, then this is going to be an annihilator of x to the k minus 1. Let me make it a k plus 1. X to the k e to the mx. And if you have e to the alpha x sine beta x, or e to the alpha x cosine beta x, right, this would be annihilated by these two, both of them, right? Both of them would be annihilated by d minus alpha the whole squared plus beta squared. And suppose if we have this operator d minus alpha the whole squared plus beta squared the whole to the k plus 1, this would be an annihilator of x to the k e to the alpha x sine beta x, or x to the k e to the alpha x cosine beta x. So what do I mean by that? Let me give you some couple of examples so you can kind of follow along. So d minus 5 would be an annihilator of e to the 5x. If I ask you what would be the annihilator of x squared e to the 3x, the answer would be d minus 3 coming off of here, and because of the x squared, I'm going to have d minus 3 to the cubed, right? Let me give you one more example. X to the 4 e to the 7x. The annihilator for this would be d minus 7 raised to the 5. If I ask you what would be the annihilator of, simply cosine 2x, that will be d minus 0 the whole squared plus 2 squared, because this is e to the 0x. That's e to the 0x, right? So because of that. And if I simplify this is going to be d squared plus 4. It's not only for this one, that works for the sine 2x as well. So if I ask you, again, we are following this rule right here. If I ask you what would be the annihilator of x squared sine 5x, the answer would be d minus alpha, in this case 0 the whole squared, plus 5 squared is 25, and raised to the cubed. So if you simplify, this is going to be d squared plus 25 the whole cubed. And if I ask you the following, and by the way, the same thing, the same annihilator should work for x squared cosine 5x2, by the way, right? Now let me give you one more example, then we'll wrap it up this section, which is the following. What would be the annihilator of this one, which is x to the 3rd e to the 7x and cosine 2x. That will be Because of the 7, it's going to be d minus alpha, which is 7, the whole squared. Because of the 2, it's going to be plus 2 squared. And because of the cubed right here, it's going to be raised to the power 4. So that will be the annihilator, and then you can let you simplify that. And that's how we find the annihilator. And this is your worksheet number 7, right? So there are plenty of problems in there. So that's a worksheet number 7. You can let me show you what that is, so you can solve it on your own. So, oh sorry, that's worksheet number 8. So try to, or homework number 8, try to find the annihilator for all of these functions, right? Try to find the annihilator for all of these functions. Let me quickly talk about how to work with, when additions. All right, so let's take a look. So what if two of them are being added? So as I said earlier, if two of them are added, if you have two of them, right, something like this, if you have one of them and then if you have another one, how does it work? That translates into the following. The addition works in the following way. So how do I find the annihilator of these two? Suppose I have e to the 2x plus 5x e to the minus x. How do you do that? Very simple. First you do find the annihilator of this, which is d minus 2. Then you find the annihilator of this. This would be d minus 1. Because of the x, it's going to be squared. And then you operate, and then you compose these two. The addition translates into composition. These numbers doesn't matter. Again, those things comes from the linear combinations. So those things does not matter. Right, so therefore the annihilator for this one would be d minus 2 composed with d plus 1 the whole square. By the way, when I say whole square, that also we mean by composition of by itself. So if you do this, is going to be d minus 2 of d squared plus 2d plus I or 1, whatever you want to call it. I'm just writing this way so you know what I'm doing. So this is going to be d cubed plus 2d squared plus d. When I operate this with respect to that, that's going to give me minus 2d squared minus 4d plus 2, which adds into d cubed plus 2d squared, and these two gets cancelled, right? And so I don't need to worry about them. And then I have minus 3d plus 2, no, it's minus 2 minus 4d. Okay, right, so that's going to be equal to, that would be the operator. That will be the operator. Why am I saying equal to? That will be the operator for that one. So basically, if you feed in this function to this operator, that's going to make this into a 0. So you can work with it and figure out all that. All right, so that's how we find the annihilator. So we'll talk about linear dependence, independence, and solutions of the higher order linear differential equations in the next video.